Welcome. This is part 21 about the Olshammar engine. Here we talk about the new intake manifold design. Traditional intake manifold designs. This is for a petrol engine with a butterfly valve first. It goes into the plenum and then it distributes to the different intake runners. And the distance of the intake runner plus a part of the plenum will cause a resonance distance, and this could be tuned for different RPMs, so you get improved volumetric efficiency for certain RPMs but not for others. You could also choose to have a wide intake runner, which is good for high volumes of air at high RPMs, but the narrow intake runner will cause the air to speed up more in the intake runner, and that improves the volumetric efficiency at lower RPMs. It also causes some whirl, which improves the atomization of fuel if you have port injection. A problem with these manifold designs is that you have air waiting for the valves to open. So you have some inertia there, and when the valve opens, it takes a little bit time to accelerate it. And this is particularly important when you have a narrow intake runner where the air needs to accelerate more. You also have the air standing still and heating up, and this is particularly a problem if you turn off the engine. Then the air in the intake runner will be very hot if you try to restart the engine. Here's a top view of this. You see the inertia and the air heating up in one of the intake runners, while the other intake runner is having air flowing into the intake valve and cylinder. Some engines are using late intake valve closing, for instance on Toyota and BYD hybrid cars. So the intake valve stays open while the piston starts coming up again, and it pushes back some of the air again. This air will be a little preheated, so you get even more heat in the intake runner. Then there is early intake valve closing, which is used by Volkswagen on its TSI engines. So when the piston is going down, you close the valve early and you get under pressure. The air cools down when the pressure decreases and absorbs some of the energy from the walls, and then it pushes up again. With the new design for EGR combined with the early intake valve closing with direct injection and the crankcase ventilation not connected to the intake, then we have only pure air with no EGR or crankcase gases waiting in the intake runners, and this could be interesting. So then we could change to the right design on the right side here, where we add a cooling channel, so we can divert some of the pure air into this cooling channel, and with the correct timing of this we can remove the preheated air in the intake runner, and we can also accelerate the air in the intake runner before the intake valve opens. This design could improve volumetric efficiency for all RPMs and allow shorter intake runners and smaller intake manifolds, which can give us a more compact engine. Consideration is that for turbocharged engines, the air can be pushed into this cooling channel, but we can only push in a certain limited amount of air because there's not too much extra air generated by the turbo. For naturally aspirated engines, we need to pull the air through, and it could be done with like a Venturi functionality in the exhaust pipe. It could also be done with a fan. Thank you very much. If you have any questions, please contact me.